Okay, so after we've pre-processed our text, the next thing we want to do is to represent the text in some numerical way. This is commonly called feature extraction. So there are many ways that you can represent your text in a numerical way. So the most simple approach is called bag of words, where you represent each text by a vector of word counts. So you can see an example here. So if you have a text that's called As You Like It, and you have a set of words in your vocabulary, the word battle appears once in this text As You Like It, and it appears 0 times in the text 12th Night, and 7 times in Julius Caesar, and 13 times in Henry V. And the word good, as you can see, appears 114 times in the text As You Like It, and so on. So if you have 11,000 words in your vocabulary, then for each word, you would have a word count for each document, and you can then imagine that you will have a lot of 0 counts, because there will be a lot of words that would not appear in one text. So you'll have what's called a sparse matrix. So in our example with the movie reviews, you can imagine that each document here is a movie review with the bag of words approach. You're just going to count how many times each word in the vocabulary appears in each movie review. You can do this with the count vectorizer from scikit-learn. This count vectorizer has a built-in tokenizer, and it also lowercases the text by default. So you shouldn't tokenize the text before you give it to this function. So when you want to use this count vectorizer, meaning that you want to have vector representations of your text where you represent the text with word count, you will have to first initiate it like this. With this count vectorizer, you firstly fit it on your training set, which means that you are learning the word counts and hereby the representations of your texts on the basis of your training set. And when you fitted it, you'll then transform your trained data set into these numerical representations. So you can do this in 2 steps actually. You could firstly fit and then transform with this function. But normally you'll just do it in 1 step, because there is this function called fit transform. And very importantly, you want to also transform your test set, but it's important that you don't fit your vectorizer on the test set, because this means that you are learning some word counts based on the word counts in a test set, but you want to learn these word counts on the basis of your training set only. So after you've run this cell, take a look at the output. So we have 25,000 movie reviews in our training set, and the count vectorizer has found 70,849 unique tokens in our training set because of its own built-in pre-processing step. It's a bit lower than what I showed in the last video. So here I'm printing what you have for the first element in your resulting representation for the training set, and it's sparse matrix, it's called. And this means that in this first element, you will have a lot of zeros, because you actually only have 238 unique words that are in the first movie review in our training set. All the rest of the words that are in the vocabulary are not found in this example. So this is a special kind of matrix called a compressed sparse row format. You can change it into a normal array that you may have worked with before. And here we can take a look at the non-zero elements by just printing the first element like this. You can see that the first element is the word with the ID called 25,459, which appears 2 times in the text. Let's have a look at what this word is that has the ID of 25,459 that we see appear 2 times. And that's the word forbidden. So a problem of this bag of words approach, and also the reason why it's called bag of words, is that the only information we have about each text in our dataset is the number of times each word in the vocabulary appears in that text. So you can imagine just all these words jumbled in a big bag, and we have no idea about the order of these words and the context of which each word appears. If, for example, we had two texts in our data set, where one text was the cat and hat, and the other sentence was the hat in the cat, then the representation of these two texts would be completely the same. One way to relieve this problem and to give a bit of information about word order back and about context is by using what's called higher order n-grams. So an n-gram is a collection of one or more tokens. You can see an example here. So here is a function for taking a sentence and making n-grams out of that. So unigrams are basically just the tokens that we've seen before. Unigrams is a collection of one token. Bigrams is a collection of two tokens. It's all possible combinations of two words in order. And then trigrams is just 3 words in order, and 4grams is 4 words, and so on. So if you think that it's important that it's the cat that is in something, and not, for example, the hat that is in something, and you want this information with your text data as well, then perhaps using bigrams as features can be a way to get this information with you. So this count vectorizer that we used before has a very easy way to include higher order n-grams. So if I write n-gram range 1 to 5 here, this means that I want a vocabulary that holds both unigrams and all possible bigrams and all possible trigrams and all possible 4grams and 5grams. So this would make a large vocabulary, but it would take into account everything from unigrams to 5grams, and in that way we can get some word order as well in our representation of the text. So let's try and fit and transform our trained data set with this new vectorizer. This can take a minute or two. So now let's take a look at the shape of this transformed data set. And again here, this defines that we have 25,000 reviews in our data set. And now you can see this very large number is our new vocabulary. You can see that when we take into account many new higher order n-grams, then the vocabulary becomes very large. It will probably have some problems with high dimensionality, and also you can imagine that it's very rare that we will see another 5gram that is exactly the same. When you go higher up, it will be almost impossible to find the same order of words appearing in the same way in different texts. So you really don't want to go too high up in the n-gram range. Okay, so in this second exercise, I want you to inspect what are the most frequent bigrams in our dataset of movie reviews. And the reason why I want you to do this is because such word collocations, as we call them, can really be descriptive of what a text is actually about. And you should use the count vectorizer as we did before, but limit the number of maximum features. And when you use this max features parameter in the count vectorizer object, you are saying that you only want to keep the tokens that are most frequent. So you're only keeping the 1,000 most frequent tokens in your dataset. And this would mean that your vocabulary would only be 1,000 words long. Okay, so another way of representing your text is by using what's called term frequency inverse document frequency, commonly known as TF-IDF. So TF-IDF is not much different from just counting terms. It's basically the same, but just with a weighing term. And in principle, you can weigh your your counts in many different ways. So TF-IDF is just one approach. So the principle of using TF-IDF is that if a word is very frequent in many documents, then this might mean that this word is not very important in general. So for example, here the word good, we saw earlier that this word appears many times in all of the text. It's a very frequent word. And because it's so frequent, we might say that it might actually not be so important. So we wanted to have a lower score. And this is what TF-IDF helps us with. But on the other hand, the word battle, if we looked at the word counts here, battle might be important because it's a word that's very frequent in few documents and not frequent in some other, which means that it might be a word that really defines what, for example, this document is about. So TF-IDF scores will weigh that higher. So before we used the count vectorizer from scikit-learn, and now we'll use what's called the TF-IDF vectorizer. And the syntax is the same as before. You define your vectorizer, you give it a name, and then you fit transform the text in your training set. But now I'm going to give you a little example about what you can do with these representations. So you can do a lot of different kinds of analysis. And one thing you can do is measure the similarity between texts. Because now the text is represented by vectors with numbers. So here I take the cosine similarity between the first movie review and all the other movie reviews that are represented with TF-IDF scores. And I here print the indices of the most similar texts and the least similar texts. As a sanity check, you can see that the most similar text should be itself. So we were looking at the text of index 0, and it is, sure enough, also the text that's defined as the most similar text. Let's take a look at what text we found was the most similar. So we can take a look at the text of this index. So firstly, I'm printing just to remember what our first text was about. It was this review on the movie Forbidden Siren, which is based upon our PlayStation 2 game. And the most similar movie review is found to be this one. And we can see that this is also about a video game. And it's also quite long, it's very long. And the least similar text is this very short one.